only through chat. Our next webinar is Professor Sri Ramarao lecture on pile draft foundations on 31st July at 11 a.m. by Professor V.S. Raju, former director IIT Delhi. Now I hand over the session to Virendra to introduce our today's speaker. Virendra, please unmute yourself and introduce our resource person.
Thank you,
Virendra.
Nagmohan sir, for the opportunity. Good morning to one and all. Professor G. Venkatappa Rao obtained his BSc from Sir CRR College, Eluru, and BE in Civil Engineering from BITS Pilani in 1966. After completing Sir Masters 1968 and PhD in 1973 from IISc Bangalore, Dr. Rao had a distinguished career of over 3 decades as a faculty at the Indian Institute of Technology, Delhi, serving as professor and head of the department, dean of students. He guided 24 PhD and over 100 MTech theses while authoring over 200 research papers, of which many have won awards for best thesis and best papers internationally. He developed and initiated the very first geosynthetics laboratory in the country and the first master's program in transportation engineering at IIT Delhi. His first book on engineering with geosynthetics, published by Tata McGraw Hills, New Delhi in the year 1990, has received international recognition through NHI FHWA USA. He was the president of Indian chapter of the International Geosynthetics Society and chairman of the Bureau of Indian Standards Committee on Geosynthetics and the recipient of many awards of the International Geosynthetics Society, Indian Geotechnical Society, Institution of Engineers India, and CBIP. Dr. G.V. Rao, after voluntarily leaving IIT Delhi in the year 2007, has documented his experiences through several books co-authored with renowned experts practicing engineering. He also served as an independent director at Econ International Limited of Railways, Government of India during 2010 to 2013. Over the years, he is involved with projects of many institutions such as NHAI, NTPC, NHPC, Ratnagiri Gas and Power Corporation Limited, Chhattisgarh State Electricity Board, L&T Geostructures, Mega Engineering, Jaipur Development Authority, and the geosynthetic industry. He was closely associated with JICA project on instrumented embankment on BCS, Japanese high-speed rail project from Sabarmati to Mumbai. He is currently the national consultant to Kalpsar project, Government of Gujarat. He also served as an advisor to MOT research project on jute geotextiles at IJRA, a center of excellence of Ministry of Textiles. Since January 2016, he is associated with IIT Gandhinagar as guest professor. In 2018, he founded, along with senior experts, the Geosynthetic Technology Advisory Services, LLP Jaipur, as its director and chairman. Currently, he is closely associated with Landmark Material Testing and Research Laboratory, Jaipur, as advisor R&D and head, Geosynthetics Division. He serves Sri Anga Bharadwaj Trust Hyderabad as its founder and chairman. Once again, I thank Mr. Nagmohan Garu for giving me this opportunity to introduce such a gigantic personality. Now I'd request our honorable speaker to please share his screen and start your presentation. Thank you, sir.
Am I audible?
Yes, sir.
Hello. And the screen is shared?
So, screen is shared.
Thank you. Good morning, everyone. At the outset, let me heartily thank the IGS Guntur chapter through Dr. Moval Ramarao Garu and associate with Professor Nagmohan and Mr. Pavada Virendra, who has kindly introduced me for this session. I think IGS Guntur chapter has made a mark for itself in arranging so many webinars almost regularly every day. And probably some people got used to that, like newspaper, that they would always set apart the time and listen to the lectures and enjoy the variety of situations and solutions which the experts the world over and throughout the country have shared on this platform. I, for one, am glad to be there today for this session, which is 54th on the line. I'm sure many more are going to come, and probably in the times to come, we will hit a century also. Now, one thing is there, which we all know, that our subject of soil mechanics foundation engineering, which today we call as geotechnical engineering, is a very wide discipline. There are many kind of soils, and there are many kind of issues which are there, and many solutions are also available now. And so whoever gives a lecture on the subject, naturally it's incomplete. It only concerns only their viewpoint or some small viewpoint only. For me, I started understanding this under the able guidance of Professor A. Sridharan when I started my research on understanding the physico-chemical forces between soil particles, in which I chose out of the 5 soils, black cotton soil is one of them. So my interaction with black cotton soil maybe should have started there, but much earlier, of course, I belong to West Godavari district. I am familiar with the soil and its issues which are there. And since childhood, I've been watching what is disaster which it really caused. The black cotton soil really caused on the structures. That apart, we also come to know through various organizations of the United Nations that the loss to the system, to the infrastructure around the world is almost next to only the old loss on floods and floods and dry climates actually. So that is the kind of loss which we are facing on this now. And that way now, to have an idea on this, I think it's better to revise some of the fundamentals which we had with us on the subject now. And as I said, only some typical ways of looking at this engineering solutions on black and soil presented in the ensuing 40-50 minutes. So to begin with now, one always wonders actually, what is this black and soil actually? Well, I happen to be, for the JICA project going beyond Bharuch actually to a place called Amod, along with the Japanese team. And I found there actually what we now call as black cotton soil. So you see the black soil and we see the cotton plantation. So that is how the origin black cotton soil has come, because the world over we call them as expansive soils actually. In India, of course, we call them black cotton soils. And in fact, before that, it was very difficult for us to realize that one of the most common crops which is grown over there is really black cotton, is cotton. Of course, in our parts of the country, we always also grow paddy very commonly, and naturally, we all know both in the eastern West Godavari districts, Krishna district, and of course, Guntur district, we have paddy the main crop. Of course, many other crops are there, but we are associated with the soil conditions for paddy as the black cotton soil. So when you go there, we also understand, of course, the basic nature of the material. One, of course, it swells considerably, and then swells and heals, and then, of course, it shrinks also very much now. And when you try to see the particles of this now, particles are hardly visible basically. We'll get onto this under my ultra microscope when we start treating them actually. So with this insistent swelling and contracting behavior actually, we find many damages occurring actually throughout the world. We know that even pavements actually are completely swollen, and disaster on the buildings also. And for example, this kind of disaster is very common actually in these at least this of Andhra Pradesh. It's very common knowledge actually that the lighter structures subjected to more damage, and probably 3 or 4 stories and higher, they're little damage now. So this is something which is common knowledge to all of us in this area of Guntur and neighborhood. But we also know that actually 2/5 of our country has got this black cotton soil. Naturally, we have in very commonly in Gujarat and Maharashtra. We also have in Telangana. We have in Andhra Pradesh. We also have Karnataka. We have soils around these parts actually near Trichy. Also black cotton soils. We have black cotton soil in Kota, Rajasthan. So it is I should say, national issue on which I venture to say that not much attention is being given to really attempt at the correct and economic solutions on the subject now. As students and faculty interested in understanding the black cotton soil, we know for one thing that if you look at the surface area of a gaulonite particle, which is commonly in most soils actually, its surface area is hardly 10 to 20 meters per gram. And then on the other hand, when you go to the montmorillonite clay mineral actually, which constitutes an important part of the so-called black cotton soil, we find the surface area is going to be so high, 700 to 800 meters per gram. And that is because water can get into the interlayer surface also. If you really look at just external surface of a big particle, natural surface area is only maybe 50 to 120 meters per gram. But when once you consider the interlayer surface also, this area increases so fast. For example, if you just consider that it's 100% monopolar bentonite, we find that 1 gram of material with having such kind of surface area can probably cover the entire football court. Can you imagine now? If you're able to take out each and every particle of 1 gram of this material, it can spread such an area. And this, along with the electronegative charge of a given particle, causes all the issues which are going to discuss very quickly. Now, we all know that the origin of this material, of course, is Plug and Trap in India. It's basaltic in nature. And naturally, there is a profile which is formed actually, and the topsoil being the blackened soil. Though we call them black, it can be dark gray also. In very rare case, it will be also brown, basically. It comes in many hues, but not really pitch black always. And then below that, usually, is a yellowish, brownish, sandy silty soil. And again, depending upon this amount of weathering which has occurred, these yellowish other colors actually come in because of the presence of cavernite there. That means same weathering profile actually is actually giving us a black cotton soil kind of thing at the top, and below that is of course going to be some kind of cavernitic clay, cavernitic material with which associated with silt and sand, and then there is of course a weathered rock, and then parent rock is the basalt, basalt actually. Now, this is one thing which we know, of course. This is when it is staying at the same place, actually, when it's staying at the same place as it is made by nature. So that is what we call as a residual soil. So when you're talking of the presence of black and soil in almost all the states of India, notably in Gujarat and Maharashtra, and Andhra Pradesh and other areas, and Karnataka, and of course, as I said, Kota also, we find that for some of them, it's going to be a residual soil. That means it's formed and stays there at the place where it is developed, where it is become weather point. What about the transported soil actually? So we find that when we try to go in further, actually, we find that this yellow clay and all yellow material, as I said, black and soil is there at the top now, and then below that is yellow or red soil, and then of course the contrast. That is general profile thickness in blackened soils, as evidenced by Professor Kattu, who has done human work on subject for almost 3-4 decades actually. He finds that the thickness of this blackened soil could be up to 10, up to 20 meters. So it's not very common. For 4-5 meters very common, but then 20 meters there minimum could be 0.5 also. And then the yellowish red soil below that is going to be around 1 to 10 meters thick. Below that is a duck and trap now. This typical profile as given out by Professor Kattu. And if you try to look at that now, all these soils which are looking at a very dark one are of course very deep soils. And then all these square patterns actually are near surfacial, you can say. That means 4-5 meters now. But we also find these patches all along the coast actually. So these are what we call transported soils. I mean, through the naturally the rivers of Mahanadi, Godavari, and Krishna, and other mighty rivers now, all this black soil probably over geological times has been transported to the coastal area, and it was there. So whatever we call in Guntur or western East Godavari districts of Andhra Pradesh, they are all actually, we can say, transported soil. That means they are not really formulated. They are only they transport somewhere else now, and that is why the foundation material, foundation rock, is essentially granite kind of rock actually. And so our soil has not come because of weathering of granite; it became weathered by the somewhere else and then transported here now. A lot of data exists actually about the liquid limit. It could be 53 to 90%. Like this now, we have all of them. But most important thing is that plasticity index could be between 18 to 53%. And we all know that basically that higher the plasticity index, naturally the problem is going to be more and more. And shrinkage limit also could be quite high. So these properties are very well known to all of us. So I'm not going to uh, get in detail of that now. So one thing is there are 3 ingredients generally necessary for finding out what is the potential damage due to the swelling. One, of course, the presence of the monomagnetic in the soil. Higher the percentage of monomagnetic clay mineral, higher is going to be activity. That means higher is going to swelling and naturally resulting back in shrinking also. And then the natural water content must be around the plastic limit. Actually, if the that is one thing which is going to be very common. And then, of course, there must be a source of water for the potentially swelling clay. This is most important. In many cases, wherein earlier the source was not there, the soil was behaving like any other soil, either clay. But then once there is a nearby source of water now, naturally it causes the swelling to occur so much now. And people have tried to classify the expansion nature now. There's a lot of literature on that now. So, for example, more recently, Holton Wax has brought out a small table from the ESBR and other kind of agencies actually. We find out from the colloid content, from the PI and the shrinkage limit, what is the kind of probable expansion in percentage of the volume, original volume actually. And in these cases, let us say, when the colloid content, clay content, 1 micron, find the 1 micron is more than 28%, PA more than 35%, shrinkage limit less than 11 now, the swelling is going to be more than 30%. And then, of course, for a colloid content of less than 15%, for a PA less than 18%, for a shrinkage limit of slightly more than 15%, we find that the probability of expansion is going to be definitely quite low. And so they are not going to be as problematic as these soils wherein there is a lot of mortmonite actually. So that is something today we know. And there are publications on this also, basically, which give us this kind of thing. But these are only estimated classification, probable expansion. Mind you, it's always the swelling pressure which are going to talk of emerging from the swelling nature is always going to be site specific. For example, when I did my PhD long ago, so this is kind of curves which are going to get from what we can call as like consolidation pressure value, E log P curves actually. But these are on compacted samples of black cotton soil. And you can say, of course, I use earlier units of pounds per cubic and all, but I don't think so. At a given density, at a given initial moisture content now. So what is happening is this pressure given in you can say gauge per centimeter square 0.125, 0.25, 0.5, 1 kilogram per centimeter square to 8 kilogram per centimeter square. What is it you find is that I have taken a sample which is let us say compacted at this initial water content and at this density. So when I'm just trying to apply the consolidation pressure now, without any soaking, without water being made available. So this is the kind of picture which you are going to get now. It just compresses actually like this. Whereas you allow this to soak actually from here. That means you put a lot of water in the consolidator and allow this to happen. It may take weeks and weeks and weeks, but at the end of the day, we find that we started with a water ratio of 1.2, and then this becomes actually up to near 1.5. When you apply a pressure of 0.25 kilograms per square, and then from there, I mean, in the relatively compact condition, from there, naturally, because of this load applied, actually, pressure applied, this swelling is only up to area ratio 1.3. So then we find that at higher pressures, naturally, we find that there is a consolidation, there is a settlement now. So this picture gives us a very clear idea that, for example, if you are trying to soak it at the pressure of 4 kilometers per square, it is coming down like this. So what is that we are trying to say is that the swelling which is going to happen or the swelling pressure which is going to resulting is also going to be depending upon what is the normal stress we are going to give to that, and is there a source of water available now continuous as it is going to swell. So and lesser is the kind of pressure, naturally more is swelling now. So I have several pictures like this now at different densities and things like that, but this is general kind of trend. Lower the pressure, higher is swelling, and higher is the pressure, they will not be swelling at all. Actually, it will be probably compressing. So that is why I said light structures are more affected, and heavier structures probably are not affected also. And then someone has done actually this kind of simple test. Actually, we have a compression curve here now. He simply allowed this sample at dry optimum, and then finds that the resulting kind of water content we are going to get is 50.6%. That means a sample which is a specimen which compacted dry optimum, very dry optimum, it is actually swelling up to 50.6% actually. And here the initial water content is hardly 10% now. And like that, if you pick up a sample at the peak, actually, that is 2% weight of optimum, and then you find that all the results are actually giving you somewhere up to 42.2, 29, 30 like this now. So that means if you are going along the compression curve now, we find that the moment we are going up from below OMC to near OMC, the amount of magnitude of swelling resulting from naturally a lot of water intake is going to be less and less. And finally, we find that when at a specimen weight of optimum, we find that this blue point, we can say that this is only around 20% actually. So the heave potential of expansion is also greatly diminished by conditioning near surface layer to the weight of optimum moisture content as we here now. So if we got the sample compacted, weight of optimum, it's going to be good. That's why even the ministry also feels, Ministry of Surface Transport and IRC feel that if you are compacting 2 to 4% plus OMC, naturally the swelling is going to be more reduced actually. So otherwise, it's going to be, if you are compacting a dry optimum, naturally the swelling could be as much as 51%. If you are compacting wet now, naturally it is becoming 9.5%, I mean 20% roughly. So that is the kind of magnitude which we have to expect actually. So then, of course, a lot of studies have been done by Professor Gatti and his workers, co-workers for almost a few decades. And what is it we find is that we find that if you are considering a given location in the field, you mean, and if you are considering the depth of the sample in centimeters, and what is the density now, so naturally we know that this is going to be varying actually with respect to the seasons. The seasonal variation is what we are going to repeat here now. So these dark points will give you rainy season, and then this whole circle actually is going to give you summer season. So we find that the density is going to be definitely high in the summer season, and density is going to be low because water content is going to be high in these districts now. And so this is what we know actually. More recently, I think probably in a conference held in 1921-9 or 2018, I don't remember now, in Delhi on geodetics of transported structures, actually, Mr. Sanjay Gupta and Sundaram has presented an excellent paper on such variations actually when they studied, when they did geological investigation for many black corn soils of the at least Gujarat region. So similar kind of behavior is observed actually, that we find that the moisture content is varying very heavily, but then as you go with the depth now, it is decreasing. And then naturally, the variation is going to be other way around, near dry in the rain season, and then it is going to be slightly increasing. So this is cyclic variation which is going to be there, and that is presented very well by in the Bowles book actually. Most of us refer to the book by Professor Bowles. And here is the depth and here is variation now. So this is going to be seasonal. What we are trying to observe as mass content variation is going to be seasonal basically. Mass content, thereby the density variation. And then if you're looking at the seasonal variation over many years or decades actually, we find that this point, at a point of no further mass content variation actually, you can say point of equilibrium wherein the depth at which we are not going to have any further change in the mass content, or naturally mass content change means no swelling or no shrinkage. This is going to give us basically a situation wherein we are going to look at the optimal condition or the worst condition in the decades to come. And that is what is we consider that if you are going to have foundation below this point of saturation, you can say, or point of which below which there is no further change, naturally, that is the most ideal kind of solution. But we find that this is not necessarily ideal, but then definitely there is one important factor that we are going to consider the stabilization zone and many things are going to be there. So long back, Professor Broms and many others have always said that in this kind of soils now, because seasonal variations, even for normal clay soils, our foundation should be below this depth actually, below the depth of roots and things like this now. And then frosty, change of groundwater level, internal erosion piping, many things are there. So the foundation depth has to be naturally, as you said earlier, if you are going to put a foundation, naturally it has to be much below an annual kind of thing. But if you consider for a decade or so, the worst point we have to find out actually. And that is the issue which we are going to see. Now we have to also understand how this is occurring basically. How this is occurring basically. Occurring means really, we all know that when we talk about the surface area, we said the surface area, the specific surface area of any clay particle, in this case, monotonate clay particle, which is going to be the reason, the cause actually for the swelling to occur now. Every particle in the nature is always naturally electrically static. The surface of clay particle is negative charge, you can say, arising from the formation of the bonds between the various particles now. And this negative charge is satisfied by positive ions, cations on the surface now. Now, so long as they are there, the particle, of course, is there's no electrostatic current there now. It is actually in the equilibrium actually. There's no net negative or positive charge, because positive charge is satisfied by cations sticking on the surface of the clay particle actually. So this is one thing we have to keep in mind, that originally in a dry state now, all the cations are just sticking on the surface of it, despite the fact that the negative charge within can be from not just surface, it can be from anywhere within the clay particle itself now. That's the first thing. Once you are going to place in this entire particle, dry particle in water, let us say in a beaker of water to begin with now, we find that these negative particles which are there at the surface now start moving out actually in water now, the negative charges. Why? Because the negative charges are attracted also by the dipolar water molecules now. So these water molecules coupled with the cations actually will start moving basically. So some of them are going to stick to the surface, some of them are going to diffuse actually. And that's why we call as a diffusable layer. That means one layer is almost sticking near the surface of the clay particle, and then the other layer is actually diffuse layer. So we always look at what thickness of diffuse double layer, which is going to be cause for all issues which are considering now. So if you look at the distribution of these diffuse double layer, that means water molecules coupled with the cations now. If this is a clay particle, blue one is a clay particle, and then if you're looking at the distribution now, naturally there's concentration, heavy concentration of the particles, okay, I mean cations right on surface of water now, and this is going to decrease actually. The distribution is going to decrease till we reach an equilibrium, and wherein there is no the water can flow easily between the two particles now. So it is this thickness is going to be important to us first of all. How is thickness important now? So this is of course decided by studying, let us say, clay colloid chemistry, whose principles we always understand and then apply in our soil mechanics actually. So we find that the thickness of the diffuse double layer which are considering, which is important for us to consider the swelling and other kinds of aspects now, is a function of many parameters, but two parameters are most important for us. One, of course, is valence of this ion actually, the cation I mean, and then of course also the concentration of those this one now, the concentration with valency and then the concentration of the that is N0 cation concentration. Now, one thing is clear now. If you talk of valency now, for example, sodium has got valency 1 only, in which case, naturally, that's occurring here now. So we find that there is sodium is valency 1 only, and where is occurring now? Valency is here now. So we can always find out that with sodium valency is going to be there, this thickness is going to be large actually. And then whereas when once the actual charge is going to be more, when the amount of cations are going to be more, or when the charge is more actually, again we find thickness is going to be more now. And this is the basic principle on which we are going to understand what the difference between the sodium and calcium and things like this now. So anyway, to begin with now, irrespective of what is there now, there is of course a diffuse double layer formation on one particle. If we assume that the model is going to be parallel plate now, we also have similar kind of distribution now. And when they come nearer, so it is diffuse double layer of this particle and diffuse double layer of this particle actually will interact. Actually, because they become naturally like charges or like poles, they repel each other now. So repulsion is being caused when these particles try to come nearer. And then if repulsion is going to be more, let us say, the particles will be thrown away. They're thrown apart now. So there is a sort of equilibrium which is going to occur actually. If you look at the interparticle forces, basically, one is between every particle and particle, there is always a van der Waals attraction. Then the distribution of these cations actually and the formation of these forces are considered as two things actually. One is what we call as double layer repulsion. This is called diffuse double layer now. Repulsion which is occurring here between these two are interacting is called diffuse double layer repulsion. And then between unlike charges, there is always a repulsion. There is always attraction now. So this is actually studied in great detail by us also in the beginning when I started my PhD. And this DLOO is a Deliagan Landau very Warburg theory. So only those who are interested in understanding this should get into this now. But point is that we are talking about the formation of diffuse double layer now, and the repulsion between diffuse double layers and parallel particles is going to cause this repulsion actually. Repulsion between these things is going to cause now. So what is it we are going to do now? If you are going to have an ion, I mean, if you are going to have a univalent kind of material like sodium as original cation here now, as well cation here now, thickness of diffuse double layer is going to be more, and so the repulsion is going to be more now. And once you are going to change this sodium to potassium, let us say, or sodium to potassium or calcium, let us say, calcium is going to be causing us a reduction in the diffuse double thickness now. And so that is going to be causing less repulsion because the diffuse double layer is going to be thinner actually, repulsion is going to be smaller because of, and unless they come nearer, it's not going to happen anyway. So these are the two things which you have to always keep in mind. The concentration, how much is what is the amount of charge which are going to be there, which means that in our case, how much monazite is going to be there. So in this fundamentally, we have actually the action of lime between in this clay soil is going to be of paramount importance. What is paramount importance now? For example, you mix some lime to the black cotton soil. So initially, there's always mixing we are going to do. Some initial stage will be there, and that initial stage will be slowly causing after a week or so. I mean, during a week or so, what we call a gel phase. That means there is always this lime particles and the clay particles are in gel phase basically. So gel phase is what we are going to discuss now. What exactly is the gel phase really means? There is an attraction or repulsion between the solid particles and the lime particles actually, and slowly, when time is going to be very at least near a week now, it becomes Neolithic stage. That means it's going to have several bonds which are going to be stronger and stronger, and the strength improvement will be going up to even 360 days also, beyond that also. That is why we find that use of lime mixture actually as a mortar. Basically, we have structures which are standing for years and years, hundreds of years. That's why, because of this Neolithic stage actually. And then when it's exposed to the air, basically, the same lime is going to become carbonate, actually cash carbonate, and then that means the reaction power is lost now. So we have this initial phase of gel phase, and we have the Neolithic phase. Let us see what exactly they mean to our construction. So if you're looking at that now, we're looking at fundamental forces as we thought now. This is an exchange. For example, there is a sodium or potassium ion on the original clay surface, clay particle surface. If you're adding lime to that, natural lime has got calcium, it's a calcium oxide or calcium hydroxide. And so this calcium naturally will easily replace the sodium. And so what is this divalent ion is going to be replacing the univalent ion. So the thickness of diffusible is going to be smaller. And so we'll see the effect happening that is going to now cause this kind of thing is going to cause flocculation. Flocculation really causes actually particles now to come nearer together actually in a way in which we'll see. And then in course of time, as I said now, it is really going to bond also. That means initially they just formed and come nearer together. Now there is a bond which is going to form. We'll see exactly what this bond is. So there is cementation now, which is going to take place maybe within a week, but then it will continue for almost a year or more also. And then carbonation is going to be damaging to system because whatever calcium oxide is available to us is combining with naturally oxygen and water, and so this is becoming back actually calcium carbonate. Actually. So that is what is going to happen with in the air. There is a carbon dioxide. So carbon dioxide and water together will help us in formulating, permanently treating the calcium hydroxide with our calcium oxide into carbonate now, which is not reactive now. So this means if a carbonation is going to be there, it's going to be deleterious to the system now. So that is what we are going to see. So before lime treatment, we find that it's very difficult actually. It's like very difficult to manage now. And then when once we are treating and leaving for after a week or something like that, it becomes actually a more lump-like now. That means the clay, very fine clay, is becoming silty, sandy size at least because many of these particles of the black earth soil have got bonded together through flocculation and maybe slowly rescinded. So this gradual hardening is going to cause, this is what picture I've shown you, these particles individually are there, and the bonding between these particles is now towermite gel, actually towermite gel, exactly same chemical which you find in cement. Cement has got ultimately the bonding force between cement and the sand particles is formation of the towermite gel. So that means the reaction product which is going to happen ultimately both in cement and lime is exactly same. There's no difference between these things now. That is what we have to remember now. That is why we had actually material which is cemented together, and these each of the lumps actually have got the gel which is formulated, and so that's why it's happening like this. So then we can see this in actual practice also. Our early students have done work on this. Reiki, I presented this paper long ago on thesis. So you look at a typical black on soil wherein the plastic index is about 30%. And clay percentage about 39% now. We combined this. We also studied silt and also flash now. So the behavior of the particle distribution of this black corn soil is around here now. And that of the silt which are taken, the silt from IIT campus, Delhi silt actually, IIT Delhi campus is around here. And then the flash which we use actually from nearby Dharmapur station is around here now. So we find that definitely the clay content in this case is very high, 39%. And clay content in the silt is rare, but it's inactive material. And clay, the ash, of course, is essentially silty sand. So when you try to look at that now, initially we just very simple test. We did examine the various other chemicals of calcium chloride and sodium chloride also, but we will focus only on the rest of the lime now. So for this black cotton soil now, we conducted the plasticity test now, and we are going to look at only liquid bit plastic bit now, and the amount of additive which is added, this lime, pure lime, is up to 8% now. We find that liquid limit is actually increasing systematically. On the other hand, the plastic limit actually is decreasing actually. So these are the two things: liquid limit increasing and the plastic limit also increasing actually. I'm sorry, both are increasing to begin with now. But when we look at that, the rate of variation of this is going to be different. For silt, we'll come back on this now. We find that the behavior actually, the plastic limit is going to be like this now. This is going to be like this now. And ultimately, we find that for comparing the behavior of black corns alone, we find that this is what is going to be the result now. The net result of plastic index with lime is going to be something like this. So what is happening is now, with an addition of a few percent lime actually, we find that the plastic in the PI is going to be reducing around 29 to almost, you can see about 18, 19 or 17 like that now. Significant reduction is going to be there. And then beyond that also it reduces, but not so significantly compared to this. Initial reduction is going to be very high. Now such reduction is not found actually in other material. What was happening in this case actually, liquid was decreasing and PL was also increasing. So together a decrease from there and increase from here causes this behavior actually of certain decrease now. We find that similar things happening with these other chlorides also, but we're not studying that at the moment now. So what was happening in the case of silt alone? If you talk of plastic index now, we find that these black spots, with the lime alone actually, these full half circles, empty circles, we find that it's here actually. Initially, it is around here, and we find there is hardly any change actually in the PI of the silt, because in that case of silt now, we find that liquid is increasing and also plastic limit is increasing. So the difference between these two will not be much with the different additives now. Even if you add 8% also, it's not changing significantly. So that is the basic point which I'm trying to say. The effect of these chemicals, particularly the lime, is going to be very significantly felt even with a small percentage of lime also. That means even a 2% lime content also, we find that the decrease is going to be quite significant. From 29, 30, it became 16%. That means the material has become workable. It becomes silt-like. It becomes silt-like. We also find another interesting feature that if you are trying to look at the behavior of, compaction behavior of the soil itself, actually, black and soil is somewhere here, actually. Whereas when you start adding lime, actually, the adding lime, let's say in this case, 6% has actually brought it, this compression curve to much below now. You find actually the MDD is going to decrease significantly, and then the OMC is also going to increase actually. So we find these changes actually, density decreasing with the addition of lime, and OMC increasing with the addition of lime. This is of course true with our normal understanding. But what is going to be important for us, I'm not going to show pictures for that because we'll lose time on that now. What is going to happen is, even with reduction in the density, addition of lime, or even addition of cement, or addition with the fly ash, all of them are going to cause an increase in the strength. Whatever you measure, you consider the CN5, you consider the UCS, you consider CBR, are becoming significantly variable even at 8 weeks also. So a summation of all of them, addition of lime, we have seen that plus index pH decreases now. If you think of swelling, it decreases significantly, compressive strength increases now, and if you think of bearing capacity, really it increases now. Significant improvement is really there. We are not having time to discuss all of them now. Same thing we do with the fly ash also. We find just addition of this fly ash on blackened soil has actually caused decrease significantly. That is there. Even with 25%, even with 20% also, we find that from 29 it came down to 20. So that means when once you are able to mix initially with difficulty, it becomes a workable material. So that is something we have to see that. So we find that in almost all the behavior, we find that the fly ash is going to give us a much better way of looking at things now. Either we think of only using lime with more and more percentage, or have a combination of lime and fly ash to do this. And this is all early work which I have done now. Now a lot of studies have been done also, long ago, years ago, I mean decades ago by Davidson, continued by Professor Kaddi. And then if you really want to design also, it's possible. There are Australian design system for use of this lime salt mixes actually in as a subgrade. And in fact, even the IRC also allows in today's document of IRC 37, latest edition, also allows you to do that now. So in the designer now, there's no change design because we are going to look at the same severe value after a certain period of treatment, and we have to find optimal lime content. And then, but it's necessary to have a good geological study to determine the dosage of lime that is there. How much amount of lime is required, we have to find out, and that is possible only if we have a perfect study. And then for a contractor, what all he has to do? He has to actually requires machines to spread the soil, to spread this lime also, and then pulverize it actually. In the days when we started this work, of course, not possible. Today we have excellent machines throughout the world, and India also, various mixing is feasible now. So when you talk of a team leader, actually, his role becomes very important. He requires a good quality of lime, efficient lime deliveries now. It is necessary to have a good primary geotechnical study to know the amount of calcium oxide which is there to obtain a given CBR or given strength actually. So to be able to do this on a job site requires, naturally we have to spread this lime appropriately, whatever we decided as per the initial studies. and then the quality of mix is important, and depth of mix is important, and then compaction also is important. So we find that now, not only finding out in laboratory what is the lime content required, but we have to see the quality of the lime in the field, and then its fineness also, which is not mentioned here, and then how best you mix it actually, and how much depth we are going to, and then are we complying with the this one. So there are machineries which are available. Number of machines we can have it now. We can have a train of equipment also. We have the original terrain. We can rip this soil actually, the surface soil, maybe 500 millimeters or more than that also. And after that now, side by of drying is there, and then they are polarized actually. And then depending upon system now, we can actually start feeding the chemical which is there, in this case lime and maybe fly ash also. Then it's thoroughly mixed now. And depending upon the initial water content which you got here now, we may wet it also, and then after doing that, actually, we spread it and then compact it, and then post-treatment, we have to also cure it actually by covering with the surface, maybe geotextile. So this process can be a batch process. It can be also a continuous process now. There are trains of equipment which is available on this now. So all this which I described is actually nearly surface treatment only. We can also think of a deep soil treatment of trying to have a lime slurry, or after having compacted quicklime bars, quicklime pile kind of thing, or we can have a lime soil piling and columns now. So these technologies are available in the country, are available in the world also. Limited extent we have also done in our country, but not in a major project now. But equipment for this doing in a big way are available now. Essentially what we mean is that if you take a lime pile now, we make a borehole actually, and then when once you make a borehole, finally, when you finally removing the water system to go boring now augering, and then you have a header actually through which you do lime actually, and then a hopper is going up, and then the top soil replaced, and then compacted becomes a lime pile. What is going to happen to lime pile now? We'll see. And then it's also possible to have the same kind of system now. As the auger is going to finally be withdrawn, actually, we also send the lime from the top now, and this lime actually gets mixed actually as the auger is going to come out actually by rotary system, and so we are having ultimately a pile, a lime soil pile. So we can think of either using slurry or using compact lime column or using actually compacted lime soil column. So in all the things now, this is deep mixing. This can be done up to a few meters definitely, and they control the sediment and swelling now. And the clay rehydration is possible now. What is happening now? You put in the in situ soil actually, and when once it comes in got the lime, what is going to happen now? Naturally, it is going to create some heat also. Through the heat, naturally, some of the soil also will be dehydrated basically, and then also any power pressure is going to reduce now, and in course of time is going to consolidate actually. So the amount of spread which is going to have, the amount of diffusion is going to have, is something we have to see in the field to decide how long we'll allow this to happen actually. So ultimately, in the course of time, as the lime is going to diffuse into the soil now, there's a long-term Bosolani effect and migration of calcium hydroxide ions now, and then of course carbonation airwards will be controlled actually, and finally, depending upon the number of these columns which are going to have and the spacing and the depth now, there will be an increase in strength and reduction in the wide ratio which is going to be there. Now all these things are covered very well in a document which is brought out from IT Delhi in the year 2000. It is a special report number 1 of IRC. It talks of all the lines of civilization, not only the clay, all the clay soils along with block and soil covered there with all the experiences. Now, what is the other lot? This is known to all of us actually, but somehow or other we have not been practicing. In fact, long back, the very first director of CRRI, Mr. Mehta, so Mehta's method of stabilization is called now, but it came in disuse. But slowly we are realizing that use of this kind of mixtures is possible now. We only talked of lemon flash. There are many other chemicals we can add into this now. Unfortunately, though this method is going to be is being popularized now, we've got chemicals of which we have no idea actually. So these chemicals are actually patent chemicals now. They work well, but we know nothing about the composition. So we are paying naturally through our nose all the costs now. But look at the pure chemical. For example, near Guntur, the Pirurala, probably Guntur district only, we have lime available in plenty. We bag of lime of 50 kilos just costs in those few years back just 100 rupees only. So we can make a survey with that now. We have to use these materials to build up our structures, foundation structures. Now. Then the geosynthetics also offer a variety of situations now. So we're not going to discuss too much on the geotextiles and geosynthetics, but two things we are going to remember. One, of course, is open geotextile. Other is going to be geogrid. And in the geogrid now, what is it we are thinking of? It's got naturally an aperture. Aperture can be having different shapes now. And the biaxial grid, it is going to be some kind of squarish kind of thing. So whenever we are going to have this now, the granular material is compact over the biaxial geogrid, particularly in a pavement or in a loader structure now. It projects the apertures, creating a strong positive interlocking. So this interlocking, which is going to be good for us now, that means by placement of these things now, we are not allowing the material to sink individually. The particles of aggregates are not going to sink individually. They will try to sink actually, and by virtue of the process of sinking, attempt to sink, naturally these bars which are going to be there, they are under tension now. So the tension is going to be transmitted to by neighboring areas through these tension bars now. So the load distribution is going to happen as the pressure distribution, and so the stress below this layer is going to be reduced significantly. So a lot of studies have been done by us and the world over on this now. The role of geosynthetics could be separator, reinforcement, drainage, filtration, and other things also. But mainly we are going to talk of reinforcement at this juncture and partially separation, drainage, and filter also, a very limited extent, very quickly. So one of the easiest examples you can think of is how to build embankments on very soft soils. For example, we'll immediately look at an experience we had developed in Chinchinada and Dindi on the coast of a sister river actually. So we find that the soft soil could be few meters thick now. There are cases when the soft soil is much thicker also. And then on this we want to build an embankment. Sometimes embankment is as high as 12 meters. So we build a geocell here actually. The geocell will see exactly. It is a 1 meter thick kind of geocell at the highest height of embankment, approach embankment to the river bridge. And by placement of this now, the theory says actually the soil here is not going to extrude it, it's going to confine between these two things actually. It is going to prevent its movement now, and we are able to make the soil work up to the ultimate limit state actually. So physical example of this is seen at that place, Chinchinada and Dindi. I told you, this is a bridge actually on Vasishtha Godavari. On this side is Chinchinada, East West Godavari, other side East Godavari, Dindi. So here the embankment, approach embankment is 12-meter high, here it is 10.5-meter high. So the kind of soil which is there, of course, is very poor soil. It has got very soft soil, you can say, and there are also lenses of sand in between. And such soft soil of black soil is about up to 20, 22 meters thick actually. On this, we are going to place a high embankment is something which you can't do unless you have some other kind of treatment. In this case, also we have reduction, we have controlled width only because 150 meters are required, and we'll find that that is not sufficient for us to construct an even embankment also. So we have 20-25 meter thickness of black soil deposit now, and embankment, I said already 12-meter high, and then we have provided a basal gypsum mattress as an alternate to many other kind of options now. And then also because the space is limited now, we have to construct a 3-meter high wall at the high end of the wall, at the end of the embankment. And then also we place a erosion control blanket. First time in the country we have placed such a kind of thing in place of pitching, which was also much cheaper than pitching actually. So what is it you find is that we can place a mattress actually by constructing geocells actually using initial geogrids now. We will not be able to spend much time on this now, but very easy to make them. And such kind of designs one can do actually very easily by using published document basically. And so make these cells as much as high you want. Normally in this case we made up to 1 meter height and in some case half-meter height now. And we're able to do this actually to create these confinement systems. These are the cells which you're talking of now. Let us see what happens now. So we provided this kind of cells, and design was done, of course, as per the then available British Standard Code BS 2006. And then this is the cell we have provided actually. And also we find that a normal embankment can't be limited as per the ministry's regulations. Naturally, it requires more than 15 meters, which is available actually. So we control this, reduce the width actually by having a small 3-meter high wall, a full panel height wall actually. And then there is also end restraint because normally it should go beyond actually. So we call it end restraint by having similar kind of mattress. And the construction, of course, is done by the Department of Roads and Buildings, the government of AP. And we find that we provided that 1 meter thick geocell actually as a foundation. And then also below that, the understood mattress was also equally thick of 1 meter at the high end up to about 7 meters. And beyond that, from 7 to 3, actually, we provide only the half-meter thick cell basically. And in other case, and this half-meter thick is also provided as understrained up to 5-meter height. Beyond that, anything is required. So that means it is done optimally, starting from 1 meter thickness of individual cell, and then below the understood cell, and then reducing it actually as we go further down actually. So this is how the geotextiles is separated in place now, and then they're building these cells actually, and this is how the cells which are made look like. And the filling also is done in a sequential fashion such that there is no wash stitching of a given product now. The material can be filled up by manual labor, it can be filled up by machines also. So we did over filling. It is in the case of 1 meter thick now, we filled up to 110 centimeters, and then we rolled it actually so that it comes back to 1 meter thickness. And then, of course, again covered the biaxial grade and then covered the nano-geotextile as a separator. And then the embankment is built. And finally, this is the wall which I mentioned at high height because it does space here. You see, every inch is very precious here now. And so this embankment, from here onward, the bridge abutment starts actually. The Sister River is the side. And what is it you find is that this embankment, because of the provision of geocell, enabled us to construct on such soils, but then does reduce settlement. So settlement is up to 1.5 meters actually. It was settling, I think, till recently. It is 20 years since it's constructed. Probably 1 meter thick. 1 meter settlement occurred. And so the surface, of course, being improved. And that's why you find these patches actually. But otherwise stable now. So what is the critical things now? No excavation and minimal site preparation. No trips required for disposal of unsuitable excavated material. No difficulty working at or below the water table. And construction 2000 now, as I said, estimate settled by 1.47. I think till recently it was settled by 1 meter. That is the kind of thing. So using this example now, we use this kind of geocells as a foundation, so as a foundation structure in many such works in Andhra Pradesh. This was not used really in any other place also, in other state also till recently. And so we have this Vijayawada wharf basically. This is the Kalisar market. This is Prakasam barrage now. And I'm talking of around 2000 basically. So what really happened was, this is called wharf road originally. And this, of course, is Krishna Eastern Main Canal, which goes up to Bandar and beyond this side, Elur. And so this was the road basically. This is the Kalisa market. This side now, one fine morning, this entire thing failed actually. It fell into the canal. This kind of material has fell down canal. So between the headworks of the canal and the other bridge now, there's 400 meters. So 200 meters fell down completely. And this portion is almost ready to collapse actually. That is the status of the system. Now what happened was, we are looking at 2000, year 2000. And 20 years before actually, it fell down the canal again. And so then they constructed obvious underground piles and did very well now. But this actually collapsed again into the canal in the year 2000 actually. So this was redesigned basically by us using the same geocell matters combination and then using a geocell reinforced soil wall with a precast panel fascia. So this was what was done now. Because of limited time, I'm not getting details of this, are published in detail and presented also. So what is it we have done is we have done a two-tier basically to make it economic and to use the reduced width also. And then one tier, the first tier is obviously just above the FSL of the canal. And so we had to do it, of course, when the canal is closed only. Beyond that, in the second tier, we try to do leisurely, let us say. And the offset also has given us economy actually. First time we two tier structure is made. And also you find that this foundation mattress actually is going into the canal also, into the canal bed also. And that was permitted by the engineering department. So this is first work which is done. First, tier is done, and subsequently the second tier was done. This is in extension to the other 200 meters now. So this is the full length of the wharf road rehabilitation structure now. And I don't say it's a beautiful structure, but it is still standing quite well, and because based upon the fundamentals which are written. Now, using these concepts of success of these geocells actually, at many other places this was done, and particularly for again the NHI work of AB 1920, the headquarters of Rajahmundry, there were two bridges to be done on the sub-rivers of Godavari before it meets the sea, Vasishta and Gautami. So there the thickness of subsoil was almost 4 to 12 meter thickness actually. Again, we tried to have minimal land acquisition because we used steep slopes. And we had coarse grained sand available in the river at the time. The contours not so much now. And that is what we have done actually, is that a design was executed wherein we have a steep slope actually. These are the slopes, steep slopes, not wall actually, but near vertical. And then a partial embankment also. And this was done. And this green one is the improved ground actually. And below that, the thickness of soil was varying in one case 4 meters up to 12 meters now. So this entire situation was actually completely analyzed by very well, using the same concept of geocell, but in a different way. They sell different cross sections further now and different heights. So the cell was not really cell as we see now. We can see this is a very high strength geotextile and filled up with the coarse sand actually. So this is what they call a cell now. So this kind of thing, depending upon the height, we had a different kind of strengths now. And so the construction was happening. This first surface layer, first bottom layer, which is placed with geotextile, and then filling up with sand now. You can see this is still the foundation, and the slopes are being constructed. And finally, you see the finished structure like this now. So what is it we have? We have this fascia now, which is not connected to the slope actually. It is separate from that now. It's actually like a stanchion which is placed. You can see the stanchion is placed in which the panels are simply slidden, like a compound wall basically, which is used precast compound wall. And anybody can go and see this. Still, is fantastic actually. No distress. It's a curved kind of thing. And we are seeing this what we call flood bank here. This is the main river actually. So curvature is possible now, and we are not any special treatment now. Construction is possible, and we acquired limited land for this also. Then same concept was used also in kind of rural roads, and you can say MDRs. In the MDR now, whenever we build on these canal roads, basically, canals were originally village roads. Now today they became major district roads. We find that after making surface now, we find that there are cracks which are coming up here. And these roads, importantly, have a canal on one side, small canal, minor canal, I can say, and then there's a waste canal on the side, like a drain actually. So when you are after 6 months of its road, actually, we find that the wavy surface is being formed, and you can see these cracks are there. These cracks are there. That means this entire thing is sliding into this. The depth of the top of this water is going to be hardly 1 meter, and the actual water is only hardly 1 to 2 meter deep now. But still, this failure is a continuous process now. So in this anyway, to make it short, the result is that the road is in terrible condition now. So they were more bothered with road rather than the failure of the canal itself now. And so initially it started with this kind of cracks, and then it became a three-dimensional road. And this dimensional road found a lot of rutting and damage terribly. So this is being a bad remark on the department. So the solution which is tried out is something similar now. We had a mattress at the bottom now. We had the panels here now. We had a separator between the existing foundation of the road actually, which is black and soil embankment, and the construction was done on the side slope of the canal actually. That was allowed by the department actually in the same construction process as it in Dindi. There's not much difference actually. And main thing is that these walls are even now also intact. 20 years or maybe more than 20 years elapsed now. The walls which are built actually are still intact. This is actually passage for washing of the cows and buffaloes actually. You can see this actually, this entry to this. So these roads don't have any more damage now. But just go behind here now, which I'm going to show you, we find that where it's not done now, again it's that bad actually. The road completely crumbles and settles into this now. So wherever they have done that actually, it is fine. And wherever they have not done it, again, the same kind of three-dimensional behavior is going to occur. This is a road from, I think, maybe Tanuku to Martyr and then Palakol actually. So same Martyr Batlanka road actually. And then other places in Jonada Mandapeta, we find same thing. You can see this wall here now. We gave them extra space. That means like almost 1.5 lanes which is given, and this is the main road actually. So we can see that these structures have been very successful in this kind of areas. Similar kind of replacement and provision of reinforcement was done in let us say Tadipalli canal crossing actually at Tadipalli, and we see that bottom. This is the foundation, partially replaced actually with sand, and then partially a geocomposite is being placed as reinforcement. And then Eluru near bus stand also, we could see that the soil condition is so poor and no working space also. So the reinforced soil walnut becomes the only solution now. And then the finished work actually you can see the groundwater level is here almost on the surface now. It's all black soil. So the replacement is up to almost 4 meters now partially. And the geosynthetic is used to as a foundation improvement system. So the point is that we can think of all the things now. All these which are covered very quickly are contained in this book, Earth Reinforcement Design and Construction, brought out by the Central Board of Irrigation Power and the International Society India chapter at New Delhi. One can get copies of that. So I refer to 3 papers actually. The Geocell we talked of, construction and the design is covered here now. And Wharf Road, as I mentioned, Vijayawada is also covered in the paper number 18. And then, of course, we come nearer to Guntur at Amravati. The roads, are constructed on variable kind of black and soil. In some cases, the swelling pressure is almost 150 to 200 kPa. And then the road was constructed for 100, designed for 100 million sand axles. And a lot of discussions on this now. Even then, we have got a prepared subgrade also. Even then, they are not confident now. So the solutions are given now by the ADCL is like this now. We can provide wherever construction is still up to subgrade level now. We can provide a biaxial grid and with a non-homogeneous separator now. And then the other layers are as usual actually. Another possibility could be that we introduce before we place the BC. That means after DBA is done now, we introduce what we call AIC, asphalt interior composite. We can do that. This is actually basically a glass geogrid kind of thing. very strong and very stiff material. So there are two occasions on which we can do this now. And as of now, they have not done many things. They have done up to on the first prepared subgrade only. And then these are being placed to the non-geotextile and biaxial grid. And then, of course, in these cases, it goes to the top without no further intervention. And if you want to place it now, we can place it the just before placing the BC. That was the way in which it designed actually, because the construction was at different phases basically. And the initially, this is of course photographs of an year back or something like that. Now the geotextile is placed, and then the geogrid placed now, and then geogrids on both sides, and this has to be anchored to the ground by using geohooks now. This is how they've been doing, and then placement of the GSB. So these are all the photographs I have actually, because beyond that I don't have any photographs. But the road is under construction. So this is how we have the solutions. Same kind of solution we think of rural roads in Bharuch now. We can see the condition of the road now, how bad it has become, so much rutting now. There's also blackened soil, soiling pressure up to 200 kPa, and within a few months these roads get ruined basically. So for this we try to develop a number of materials under the banner of the IJIRA, which is a center of excellence for jute geotextiles. So we knew that the jute is going to degrade very well in, I mean, very much in blackened soil now. So for this now, not just rot-proof treatment of jute, but also we used actually a new kind of product which we made now, blending polypropylene fibers with jute now. And this has given a much longer behavior, actually, much longer performance, and field trials are have to be done on this kind of thing. So attempt is being made for this. So whatever I talk today is contained actually for simplicity in a book we brought out, I think more than 5 years back, ground improvement strategies for infrastructure development now. And in this, the initial introduction of overview, and then geophysics overview is there, Black and Surf India, the stabilization is covered here. So whatever I mentioned, actually, quite a few are covered. And I didn't do much on this core and due today. I have just shown the latest results now. But thing is that if somebody wants to go through them, I can send a copy to YJS Guntur chapter. When one thing settled now, they can go through these books and then get more information. So the solution, of course, is I don't say very simple now. The search keeps going. And what we find is that for infrastructure work dealing with blackout soils, both conventional solutions like lime flash treatment and modern solutions dealing with geosynthetics are very effective. The choice depends upon you, a decision maker, upon the kind of location we have got, the kind of selling price which is there now, the kind of importance of the road or structure which you are going to think of, depending upon the availability of the technology for this now. So finally, thank you all, the members of the AJS Guntur chapter and all the audience actually from both the GTAS and LRL. And very special thanks to IJS Guntur chapter, Professor M. Ramarao, and the IJS student chapter, KKR and KSR Institute of Technology and Sciences, Binjanapadu, Andhra Pradesh. And thanks again, Professor Ramarao and Mr. Nagamohan and Mr. Virendra Rao. And thank you very much. At the end, I close with salutation to our beloved Guru, Acharya Akilabhadra Raja, who belongs to Ongole and who lived quite some time in his early days in Guntur, to whom I dedicate this lecture. Thank you very much. Namaskar.
Thank you, sir. Before question and answer session, I will share the feedback form. Kindly, if you fill it. Yes, I have shared the feedback form. All of you copy this and give your feedback. Now you can and type your questions in the chat box. Sir, you can also view the questions, sir.
Yeah, I can view the questions. Am I audible?
You're audible, sir.
Okay.
Participants, you can type your questions in the chat box.
Thank you, Sanjay Gupta. Thank you by being part of the audience. Hello, any questions?
Participants, kindly enter your questions in the chat box. So there is one question, sir. Are cationic stabilizers with 3 plus charges also used for soil stabilization?
uh, yeah, there are many stabilizers are available. I am talking of fundamentals basically. Some of them are commercial, some are patented now. So what I am always aiming at is why not we start from fundamentals of getting pure lime and mixing with water chemicals we want to know. That will become very cost effective. Otherwise, these things may not be cost effective also. That is what my worry is. Otherwise, many chemicals are being marketed today, and some of them come from Israel. They have got very good characteristics, and a lot of problems are done now. So hesitation for the implementer is always going to be that what is long-term behavior. In the case of pure lime, we know the long-term behavior definitely, uh, except the carbonation, which is going to make to picture. Otherwise, it's going to be increasing the strength in quite some time and remaining there. See, we see the buildings which are built 300 years back with lime plaster and lime as a mortar actually are still there. There's nothing wrong with them. The fascia may be bad or something like that, no, but work for hundreds of years. I mean, most of the bridges, the structure was built with the lime only and some additives, let us say. So it is still quite strong. So I feel that the basic lime and other treatment is going to be fundamental nature to the soil actually, and one can design a mix easily, and it requires a limited work only, very limited work and inexpensive research in the laboratory to develop a chemical, to develop a mixture. Actually, these are called hydraulic binders now. We can mix it in dry, we can mix it in wet condition. There are many ways of trying to do this now. And that is why the depth at which, Mr. Anurag Kapoor says, how much depth actually. Now, I don't think any limitation of the depth now, but what happens is that below a certain depth now, the reactivity is not required because, already we require the equilibrium moisture content. That means there's no change in moisture content. At that place, we're not worried at all. We are more at the top layers only, as I should say, top few meters only. And unfortunately, what the condition of most of the government agencies is that they remove the material. In fact, the NHA and the ministries initially say that replace 600 millimeters, Katambag. Only when it is a deep only, the problem comes now. So I will say that we'll try to use it up to 3 to 5 meters max actually. Below that, normally it's not required because there's no fluctuation in water table and there is no other major problem in the top layers actually. So that is what I'm looking at. So we can also, Mr. Sriram Marathe, if you want to study the effect of two stabilizers, how to go ahead with the testing to find what dosage. This is you see, normally for finding out, suppose we think of lime only as a stabilizer. So we have to find out the lime reactivity of the material. That means we mix different quantities of lime, different parts of lime, in a sample which we make at, say, MDD or OMC or plus whatever mass content I said, and then make the samples for unconfined capacity strength only. So you will find from these tests actually for curing, accelerated curing or curing from 4 to 8 weeks now, we can really find out what is the effectivity of this. Now that means what is the optimum value of the sand which is required for the better soil. So let us say it is 4% we'll say it's required for a lime. In the same way, we can have mixes of two chemicals also, isn't it? So we are finding out the reactivity of these chemicals on the soil and developing the strength actually. Okay, so that is the main thing now. Either we accelerate the curing or we cure for at least 8 weeks and try to see that now and get the CBR or uncontrollable strength and use it for design. But when you are using other kind of chemicals now, we have to bother about its impact on the nature also. What is kind of leachate which is going to come into the picture now? Many works are done actually at IAC Bangalore, wherein if sulfates and chlorides are there now in the soil, now these may leach out with carbonate gel, like they affect your cement actually. They will also affect lime because gel formed in both are exactly the same. So the gel could affect it actually. So the leachate word bother about that means the type of soil and chemical nature is very important. The soil in per se should not have the sulfates and chlorides. If it is there naturally, this is not the best way to do it. But then even cement is not good actually. The only issue, of course, which you are going to have will be that the leachate should not be carcinogenic. That is one of the things now. So there are other chemicals that are available now, but I have studied lime naturally as well, talking extensively on this now. Most of the other chemicals have been found to be carcinogenic, and that is why they are not being used extensively. So for, I think Mr. Mohan Ramanathan once say, for shallow soil mixing in situ up to 5 meters, there are systems with an excavator based mixer attachment in the case. Yes, sir. I think I'm not disagreeing with you. But point is that when once you want to use the excavator and all these things now, naturally, how big the job is going to be. If the job is big, yes, we can use all modern systems. Definitely, we can do that one single layer also. But do you want to compact, do you want to separate the 5 meters of soil? In the rare cases, in that case, actually. There are other methods available for treating that kind of systems, actually, like stone columns or like other kinds of things are also there. So the point is that ultimately, we are not saying that use this method only. We have to find out what is the quantum of the work which is going to be there, what the kind of structure is going to be there, and how much investment we can make on this kind of thing. Provided is a big project, yes, we can do this also. You see, even earlier having stone columns also, the job quantum of job is going to be very important. That's why not all the stone columns they are having are not vibratory. They are all manual only. Rammed stone columns we used to call them now. So here the ramming could be also, I can say, kind of manual if it is a small job. That's what I'm saying. Otherwise, I'm happy you brought out this, Mr. Ramanathan sir. I'm happy to brought out the availability of this now. But if you are excavating is okay, but we can't mix and then leave it like that only. We have to compact it also. So that's why I'm not recommending that we should do this kind of thing. We want to do deep treated treatment actually through boreholes. So I'm not saying that you do remove 5 meters soil. Where from you will place it now? How do you compact it? These issues are going to be there. And it all depends upon the equipment we are going to choose. And as I said, the nature of the material and the foundation we are going to treat it for the kind of structure which we are going to think of.
So next one from Srinivas Kasa. Sir.
Yeah, Mr. Srinivas, you say that I want to put the rigid payments actually. Number one is that before you place a rigid payment, concrete payment today, if you're talking of national highways and expressways or state highways also, thickness of the pavement itself is 37 millimeter, 370 millimeters usually, of that order. And below that, there are going to be two layers at least, like rolled concrete, rolled dry concrete, DLC, actually, DLRC, they say that. Below that also, there is a sub base actually. All of them are going to be almost 1 meter thick. So we have to evaluate what is the swelling pressure of the soil there actually, and then arrive at solution. So if the swelling pressure of the soil is there at the near the subgrade level now, I would recommend actually as offshoot, as a offhand reply, that I will actually treat the top half meter soil actually with the lime and then go ahead with the rest construction. Okay. And then usually we are supposed to have drains on both sides so that water doesn't enter the pavement actually, because the pavements are supposed to be waterproof layers also, and also got a layer of polythene below the concrete also. So if water is not entering the pavement actually, if required, we will definitely treat the top half meter soil of subgrade, and then that should do the satisfy the system.
Next one from
Yeah, will it be possible to avoid deep-seated failure as treatment? No, this is to analyze right in the beginning now. It's not the moment we have got a layer now which is stabilized actually. There are softwares available to find out the stability of the layer now. Isn't it? What is the issue? I don't see the issue. Because we are trying to avoid right in the beginning itself actually by analyzing the thickness of this of the modified soil which I've got now or any portion of geogrid now. We are going to analyze right in the beginning. All kind of values are going to examine, and which dipset is going to be important actually. In fact, when we did the work for restoration of the canals near Nagpur, naturally this was done. Provision of geosynthetic walls also was done in the canal slope, and then the deep set failure also is thought of because the failure can go through from the bed of the canal to the side of the embankment also. This has to be done as a routine thing for all structures. What precaution should one take constructing embankment dam using expensive soil? We are not supposed to construct, madam, I think you're asking me actually. We're not supposed to construct a dam with the blackened soil, is it not? Nor we can use it as a clay core. But Chitra wants to say something now? Mr. Kesarao has said that, asked the question, can we use the type of solution for reclamation of coastal areas? What kind of work you are talking, you should say, then we will be able to address that. We came across research papers where people show 360 days of curing. No, I don't think 360 days is feasible, but that's only study to show, probably to find out the effect of so-called stabilization actually, isn't it? We have to cure in the beginning only. Later, the nature should take care of. That's why we're not taking this 360 days strength actually. We're taking the strength for about, 4 weeks or 8 weeks into design. The soil is going to be stronger by the time, beyond the time actually, which are not taken into account. We are assuming, as I mentioned earlier also, that the strength is going to improve beyond 8 weeks also up to 360 days. So we are not going to cure because the design is done at the 8 days curing period, the strength only, CVR or PCS. Yeah, Prasad, nice to have a chat from you. Number one is that I am trying to say that lime can be mixed easily with clay because fundamentally relationship between the lime, that is cations of the lime, that means calcium ions, and the natural surface now. Whereas cement doesn't exhibit their characteristics. So what I am trying to recommend, though I didn't say very clearly, is that we are trying to modify the soil by using lime. And second step, we always say that we can now add the cement if we want to quick improvement to strength now, or we can add lime also. If we wait for some more time, it will give equally good strength actually. There are cases when they mix the lime and the cement, but then the initial cement is not going to get in touch or act anything at all. Because when once you add lime now, it becomes it becomes granular material now. And granular material, if you are adding cement, it's going to work very well. So it should be a two-stage process actually. That's what I feel. And once you have done now, naturally, they can work for long-term durability, so long as you don't have any chemicals like, as I mentioned, chlorides and phosphates, it's going to work actually. So thank you, Prasad. I'm able to at least not see you, but talk to you. Happy after a long time. Mr. Guru Prasad Chavan wants to find out, can you find out the efficiency of the geocell for better soil in the lab? Now, geocell has got a cell which is very large in size actually. So if you really want to find out efficacy, we need a very large tank, Like, remember whenever you do a plate load test also on the determine the foundation wear capacity or things like that. Now we use that 5B. That kind of concept is required. You need a huge tank actually. You need to find out all the things now. Then we can definitely check the efficiency. But it's not that we are going to check the efficiency for what purpose actually. So this is done for many, I should say at least a decade now. Efficiency has improved also in road structures actually. Efficiency has improved in wall structures actually. So the many studies are available now. I think first one should check the available information on the subject, and then of course definitely can use it now. And also the behavior depends upon not only the soil but also depends upon the fill material. The fill material we are going to use further. Is it aggregate? Is it sand? Is it soil? So efficiency depends upon that actually. Okay. Mr. Sriram Marathe. How to go ahead with curing the heated lab? Normally, what we do is that we make the samples actually, and over that you put some kind of sawdust actually, and then cover with a gunny bag, wetted gunny bag. That's what I do. Other way of doing is if we got a small number of samples actually, then we can do a desiccator. The desiccator normally we have a system to desiccate actually calcium carbonate or chloride or silica gel. So that we replace with water only. So once you put water at the bottom of the desiccator and place the samples are on a wire mesh actually and cover this desiccator with a lid. So the atmosphere there is supposed to be 100% relative humidity. So that is going to give you. So that is what we try to do. So thank you, Sanjay ji. Actually, I don't have the paper with me. So if possible, can you send a copy? Because, the Spenger didn't give me a copy of the publication. Nor my paper is published in that due to reasons which you know. So if you're able to give me, I think I will use it in my future presentations. It's a wonderful work done by you. I think after Professor Gatti, nobody else did that kind of field work to give us the seasonal variation, mass content, and things like that across Gujarat. Many samples have been tested by you. But please do send me a copy of the paper so that I can use it in my future presentations. Thank you, Sanjay.
Sir, Remaining messages are all thank you messages, sir.
Yeah, I think
Only from Professor B.A. Mir, only one question, sir.
yeah,
Last one.
Professor Mir, good morning. How are you? By adding lime to black on soil, water content, liquid limit, pressure level increases and dye density decreases. However, strength increases. Please clarify the mechanism behind this. Mechanism I already shown you that even when the particles are separated, actually, they are not separated basically. That's called what edge-to-face flocculation is there. That means each and every particle is in touch with the other particle in a perpendicular mode. That's called flocculation actually. Flocculation means that particles are assembled almost near perpendicular actually. So that is why the particles are not able to come together. When they are coming together, it's like a parallel bed arrangement. It's called disperse arrangement. Here, the addition of lime causes flocculation arrangement now. When once they are particulate arrangement like that in perpendicular fashion now, the density decreases. Even then, the dominated gel, which is shown in the SCM to you, is creating bondage between several particles fundamentally in a manner similar to cement actually. That's why the strength improves. So
Okay,
thanks
sir.
everybody. I think there are no further questions.
Okay, sir. Thank you very much, sir, Dr. Aparo, sir. We are very thankful to you on behalf of GS Guntur chapter for delivering the lecture, and also we have expressed special gratitude from our KKR and KSR Institute of Technology and Sciences. Hope we will meet soon, sir.
Thank you. Thank you very
Thank you,
much.
sir. Sir, you can now sign off, sir.
Yeah.
Okay, thank you very much. Participants, this is the end of the meeting, so I'm ending the session.